All right, we're at the last section, 4.6, relative velocity and relative acceleration. This is going to seem like a difficult section, but I'm not gonna make you very responsible for. I'm not going to make you responsible for problems of this type, but I just feel for completeness sake, we should discuss it. So I don't think I'll have any homework or quiz questions, but just want to give it to you. And then I'm going to assign a little video. It's an old video, but it's kind of a fun video that helps um, discuss frames of reference. Um, so here we go. Um, let's get on the right slide. Let's see how observations made by different observers in different frames of reference are related to one another. A frame of reference can be described by Cartesian coordinate system for which the observer is at rest with respect to the origin. Consider two observers, A and B, along a number line, figure A at the top. Observer A located 5 units to the right of observer B. Both observers measure position of point P, located 5 units to the right of observer A. Suppose each observer decides she is located at the origin of x-axis of the x-axis. Figure B. Note that the observers use different coordinate systems, so they have different values for point P. Observer A claims that point P is located at position with the value x of A equal plus 5. Observer B claims it is located at position with value of xb equal 10. Both observers are correct, even though they make different measurements. Their measurements differ because they are making measurements from different frames of reference. Imagine observer B in the bottom figure moving to the right along the xb axis. Observer A claims point P remains at rest at its position with value of plus 5. Observer B claims position of P continuously changes with time, even passing him and moving behind him. Again, both observers are correct, with the difference being their measurements arising from their different frames of reference. Okay, let's go to another example. You see a woman standing on a beltway. She sees a man moving with a slower speed than the woman observing the man from the stationary floor. So consider two observers watching a man walking on the moving beltway. The woman standing on the moving beltway sees the man moving at a normal walking speed because she's got the speed of the belt, and he's on the belt, and she just sees him walking normally. The woman observing from the stationary floor sees the man moving with higher speed because the beltway speed combines with his walking speed. Both observers look at the same man and arrive at the different values for his speed. Both are correct. The difference in their measurements results from the relative velocity of the reference frames, the frames of reference. Okay, now this will be a little bit complicated. This is where I say I won't make you responsible for it on any homework problems or tests, but I just want to show, if I give you a homework problem, it'll be a simple one. Consider a particle located at point P in the figure. That's where the two triangles meet at a point. Imagine that the motion of this particle is being described by two observers. Observer A in reference frame SA is fixed relative to the Earth. Observer B in reference frame SB moving to the right relative to SA and therefore relative to the Earth with a constant velocity of VBA. Let's use double subscripts for the notation. The first subscript represents what is being observed. The second represents who is doing the observing. So VBA means the velocity of observer B and attached to the frame SB as measured by observer A. Observer B measures A to be moving to the left with a velocity of VAB equal to minus VBA. Now, put each observer at her or his respective origin and define time t as the instant at which the origins of the two reference frames coincide in space. In other words, let's back up as B a little bit where it's coincident. If it's been moving, it's right where it lines up with SA and then continues moving. At time t, the origins of reference frames will be separated by a distance of VBA times t. So the velocity times the time will give you a distance. Label position P of the particle relative to observer A with the position vector RPA, and that relative to observer B with position vector RPB, both at time t. From the figure, the vectors RPA and RPB are related to each other through the following expression. RPA equals RPB plus VBAT. So you can see the VBAT. You look at the head to tail method, the VBAT is at the bottom and the RPB is shooting slightly upward. And the sum of those two is RPA. So that's how they're related. Differentiate with respect to time with VBA being constant. Or I already pushed that button. So UPA is the velocity of the particle P measured by observer A, and UPB is the velocity of B measured the velocity measured by B. Now let's use the symbol U for particle velocity rather than V. V is used for the relative velocity of the two reference frames. Now, the last equation demonstrated by the red vectors, the last equation is demonstrated by the red vectors at the top of the figure. Vector UPB, the velocity of particle at time t, is the velocity as seen by observer B. You add the relative velocity VBA of the frames, and the sum equals the velocity of particles as measured by observer A. Oops, sorry about that. I'm accidentally pressing when I don't mean to. Okay, these equations, the RPA equal RPB plus VBAT and the UPA equals UPB plus VBA, these equations are called the Galilean transformation equations. They relate position and velocity of a particle as measured by observers in relative motion. Now, although the observers in two frames measure different velocities for the particle, they measure the same acceleration when VBA is constant. We can verify this by taking the time derivative. DUPA dt equals DUPB dt and dVBA dt. But because VBA is constant, we get that it's equal to 0. So DUPA dt equals DUPB dt, which means that the acceleration of particle, the particle measured by observer in one frame reference equals that measured by any other observer moving with constant velocity relative to the first frame. So APA equals APB. The acceleration of PA equals the acceleration of PB. All right, let's look at an example. And if I were to give you a problem, it would be on the simplicity of something like this, this boat crossing the river problem. A boat crossing a wide river moves with a speed of 10 kilometers per hour relative to the water. The water in the river has a uniform speed of 5 kilometers per hour, due east relative to the earth. If the boat heads due north, determine the velocity of the boat relative to an observer standing on either bank. Let's conceptualize this. Imagine moving in a boat across a river while the current pushes you down the river. You will not be able to move directly across the river, but will end up downstream as suggested in the image. Imagine observer A on the shore so that she is on the earth, represented by letter E. Where is the letter? Oh, there's no position, but it's just the letter E representing earth. Observer B is represented by the letter R in the figure. Um, this observer is on the cork floating uh, in the river, at rest with respect to the water and carried along with the current. When the boat begins from point P and is aimed straight across the river, the velocity is UBR, the boat relative to the river, and VRE, the river relative to the earth, add to give the velocity VBE, the velocity of the boat relative to observer A on the earth. As the boat moves, it will follow along vector VBE as suggested by the position after some time in the figure. Now let's categorize this. Because of the combined velocities of U relative to the river and the river relative to the earth, we can categorize this problem as one involving relative velocities. Okay, let's analyze this. We know UBR, the velocity of the boat relative to the river, and VRE, the velocity of the river relative to the earth. What we must find is UBE, the velocity of the boat relative to the earth. The relationship between these three quantities is UBE equals UBR plus URE. You can just see that from the vector addition. The terms in the equation must be manipulated as vector quantities. The vectors are shown in the figure. The quantity UBR is due north, URE is due east, and the vector sum of the two, UBE, is at an angle theta. To find the speed, UBE, of the boat relative to the earth, we use the Pythagorean theorem as shown. UBE equals UBR squared plus URE squared. Take the square root of that. Now let's, and if you plug in the values, you get 10 kilometers per hour squared and 5 kilometers per hour squared. Take the square root of that, you get 11.2 kilometers per hour. So he's going straight across at 10 kilometers per hour, but with his motion this way and the river going this way, he's got an actual velocity, combined velocity, 11.2 kilometers per hour. Let's see. Let's find the direction of UBE, that is the angle. It's the tangent. So what is the relative to theta? The VRE is the opposite, and the UBR is the adjacent. So the tangent inverse of the opposite over adjacent, that is the tangent inverse of VRE over UBR, will give us the angle. So the tangent of 5 over 10 is 26.6. Now, let's finalize this problem. The boat is moving at a speed of 11.2 kilometers per hour in the direction 26.6 degrees east of north relative to the earth. Notice that the speed of 11.2 kilometers per hour is faster than your boat speed of 10 kilometers per hour. The current velocity adds to yours to give you a higher speed. Notice that in your resultant velocity, is at an angle to the direction straight across the river, so you will end up downstream as we predicted. Now, if the boat travels with the same speed, of 10 kilometers per hour relative to the river, and is to travel due north as shown in the figure, what should its heading be? Okay, let's conceptualize and categorize this problem. This question is an extension of part A, so we have already conceptualized and categorized the problem. In this case, however, we must aim the boat upstream so as to go straight across the river. Let's analyze this. The analysis now involves the new triangle shown in the figure. As in part A, we know that VRE and the magnitude of the vector UBR, and we want UBE to be directed across the river. Notice that the hypotenuse is no longer UBE. UBE is now the adjacent side to theta. We use the Pythagorean theorem to find UBE. So UBE is equal to the square root of UBR squared minus VRE squared. In other words, it's the hypotenuse minus the opposite. You take those, you square those, and then subtract it, and you take the square root Uh, so 10 kilometers per hour squared minus 5 kilometers per hour squared, you get 8.66 kilometers per hour. And the direction is the tangent of the opposite over the adjacent. So it's 5 over 8.66, and you come up with a value of 30. The boat must head upstream so as to travel directly northward across the river. For the given situation, the boat must steer course 30 degrees west of north. For faster currents, the boat must be aimed upstream at larger angles. Okay. Imagine that the two boats in parts A and B are racing across the river. Which boat arrives at the opposite bank first? In part A, the velocity of 10 kilometers per hour is aimed directly across the river. In part B, the velocity that is directed across the river has a magnitude of only 8.66 kilometers per hour. Therefore, the boat in part A has a larger velocity component directly across the river and arrives first. Now it's going to be downstream, but he will arrive on the other side of the river first. Okay, this ends our discussion of motion in 2 dimensions. I will have a little bit more, another video, a fun video on frames of reference.